let's discuss graphing the derivative. Remember, the derivative means slope of a tangent line. So here our goal is to graph the derivative given a function f of x. Start with the easiest part, where f of x has horizontal tangents. That's going to be where the zeros of f prime of x are, the derivative. Then we'll look for where the function has positive slope or negative slope. Remember, slope is the derivative, so then our derivative will be above the x-axis or below the x-axis respectively. Finally, if there's any discontinuities, cusps, vertical tangents, places where the derivative does not exist, that's going to give us holes or asymptotes. Let's take a look at some examples. Here we are directed to use the graph of f of x below to graph the derivative f prime of x in the same coordinate plane. Sometimes we need to graph it elsewhere. So remember when it says graph f prime of f, we want to think of ourselves, graph the slope. So first example, a constant slope graph. This has a negative slope. The line is going down, and it's not changing how it is. If we were to pick 2 points on this line and count the slope, which if we actually had grid marks, we would count it, we would determine the value of that negative slope. The fact is that's always a negative slope, so if we are graphing slope, the values of it, we're going to find a negative value. So negative is below the x-axis. So we're going to pick a point that's below the x-axis and draw a constant value the whole time. If I were to pick a point here, it has the same slope as if I were to pick a point here, it's the same slope, or pick a point here. All of it is the same slope. Now remember I mentioned you want to start where the function has horizontal tangents. This one didn't. It was simpler. It always had a negative slope. Let's look at a graph that has changing slopes. When it has changing slopes, then we need to look for where the function has horizontal tangents. So I see a couple of places. Here's a place where if I were to draw a tangent line at this max, it would have a slope of 0. Or at this min, it would have a slope of 0. So I find on the x-axis and put a point. Those are the zeros of my graph of the slope values. I am graphing the slope. Let's change this to slope values. Over here, slope is 0, so it's 0 on the derivative graph. In fact, let's call this f prime of x if the original is called f. Here the original is called f, and once we graph our f prime, we'll label it as such. So again, this was a slope of 0, so the f prime value is 0. Also a slope of 0, so the f prime value is 0. Now we go to where there's positive or negative slopes. Now this is just an estimate. We're just estimating it. So before this horizontal tangent, if I were to draw a tangent line, now I don't know exactly what that slope is, especially when I don't have numbers or grid lines, but I can tell that the slope is a positive value. This slope is greater than 0. So when I graph a point, it's going to have to be above the x-axis. Similarly, over here, if I were to pick a point, and this is just any point past this horizontal tangent, this also has a slope greater than 0. So it should also be a point above the x-axis. Now this slope looks the same as this slope, so I'm going to plot this f prime value at the same level as the other. Now I'm going to pick a point between those two horizontal tangents so that I get a good taste of everywhere. Graph a little tangent line, and now that has a negative slope. The slope is less than 0. So I'm going to plot a point that's under the x-axis. Remember, this is an estimate. Now I'm going to connect the points with a smooth curve. And here is my f prime graph. Now just to not confuse myself, the f graph was this first curvy one. The f prime graph is this parabola-shaped one. Let's take a look at when there is a vertical tangent. So I'm going to look for where I have horizontal tangents first, but I don't really see any. Now this is close to being a horizontal tangent right there. So I'm going to say about this point, it looks like the slope is close to 0. Almost 0. Maybe we'll say approximately 0, but it's not quite there. It's a little bit over because it's positive. Let me change that to my blue because that's graphing the derivative. So it's slightly over 0. Down here, if I drew a tangent line, it also looks really close to 0, but still also kind of positive. So it's going to be right here. Now, as I move to the right, what's happening to the slopes? They're getting definitely positive. And right here, also definitely positive. So something greater than 0 would be the slope value. Similarly here, and it has what looks to me like the same slope that I just used. So about there. Now notice what happens as we get closer and closer to this vertical tangent right here. As we get closer and closer, the slopes get so steep that now it's vertical. And remember that where there's a vertical line, the slope is undefined. So at that point right there, the slope does not exist. But remember what we said, as we approach that point, these slopes were getting steeper and steeper and steeper and steeper. Same thing coming from the other side. These slopes are getting steeper and steeper and steeper and steeper, more positive. So what's that going to look like if we connect the dots, connect the points? What kind of characteristic does that look like? That's right, it looks like our derivative has a vertical asymptote in there. So here's f prime if our original graph is f. Let's look at a few more. A discontinuity. Well, let's do all the other things that we normally do. Find where the slope is 0 and graph that part first. Now if I come to a hole, there is no slope there. At this hole, the slope does not exist. So if I'm graphing the slope values, I don't have a value at that point. Now, coming from the other side, this is a very shallow slope. So at that point, the slope is almost 0, but kind of negative. As I go to the left, the slope is more obviously negative. And as I get even farther to the left, it almost is like that vertical tangent scenario where the slope almost does not exist. So what does that mean? Well, where I have the slope negative but close to 0, I'm going to put a negative function value. Where the slope is negative, obviously negative, I'm going to go a little bit lower. As I get closer to this discontinuity, it got steeper and more negative, so it's going down like that. Similar to the previous graph, it's like we have a vertical asymptote because it's like we have a vertical tangent. Let's look at a cusp with a changing slope. So again, I don't see any horizontal tangents, but I see here positive slope. The slope is greater than 0. As I move to the right, the slope is still greater than 0, but even more so. So I'm going to start plotting points that are above 0, and then even more so above 0. And then as I move to the right, even more and more and more. Now at this point where there's a cusp, remember the slope does not exist. But if it's a changing slope where it looks like it's getting steeper and steeper and steeper, that means that we're going to have something like an asymptote. Now coming from the other side, what do the slopes look like? Here, the slope is less than 0, negative. Here, the slope is less than 0 again, but not as negative as it was here. So we're starting very negative and then getting less negative and less negative and less negative, and I don't really know what's happening after my graph stops, so I'll just do what I can. So again, because of the drastically changing slope that almost looks like a vertical tangent, we're going to have an asymptote in the graph. Finally, let's go ahead and label f prime and f, and f and f prime. Finally, a cusp with a constant slope. Now again, I don't have any horizontal tangents, but I like the constant slope. That kind of makes it easier. Here, a tangent line, the slope is negative, less than 0. So I'm going to find a value and plot a point less than 0. Now this entire line has that same slope, so no matter where I measure the slope, like maybe over here, it looks like it's the same. Well, it is. It's a line. So my slope value is at the same level. In fact, everywhere it's at the same level until I get to, oops, sharp point. What's true about a sharp point? The derivative or the slope does not exist. I cannot draw a tangent line there. So if I'm graphing the derivative, I'm going to show a hole. So let's see what happens after that cusp. Now I draw a tangent line and the slope is positive, but because it's linear, it's the same positive value. So I can graph a positive value. Now, the negative value and the positive value look like they should be the same value, just negative or positive. So however low I went here, I should go that amount high over here. And the same thing no matter where I pick a point. And they break apart at that cusp, so that's where I'll stop. Pretty cool, right?